Hello, my name is Nathan Cohen. In this video, you're going to see an exciting and surprising demonstration of an invisibility cloak. We're going to show you how to get front scatter around an electrically large metal wall by using fractal metamaterials. You won't find this in any textbooks, so be prepared for something new. The heart of invisibility cloaking is front scatter, the ability to have waves go around an object to the other side. If you have a large metal wall, a metal monolith, this is extremely difficult and is done feebly through edge diffraction. However, the front scatter is so low compared to the direct, unobstructed path, there's virtually no front scatter using edge diffraction. So how do we get around this and generate front scatter? Put simply, we generate substantial front scatter by using our patented fractal metamaterials to make a looped manifold that covers a metal wall. Fractal metamaterials generate evanescent surface waves which travel along the fractal metamaterial manifold and around the wall to the other side, and then decouple to a traveling wave. We don't go through the wall, but around it. The physics is well known, but this clever application makes for fascinating results and a new field of applied science. Here's a diagram. The metal wall is cloaked by slipping on a two-layer cover of fractal metamaterials. Each layer is separated by an air dielectric, in this case styrofoam. The wall is metal and nothing gets through it, but the cloak slips the waves around it. Here's some particulars on the dimensions. Note the cloak is very large compared to the wavelength, which is at S-band. So here's the demonstration. My colleague is using a network analyzer with S12 to measure the direct path intensity between two well-spaced log periodics. Note he's holding up a ruler to show you what one wavelength corresponds to here. Frequencies between 2.5 and 3 gigahertz. The separation of the antennas is very large compared to a wavelength. And now he's going to do the calibration by normalizing the intensity between the two antennas with no obstruction. Steps are 5 dB, and this now constitutes the direct path. Any obstructions will cause the measurements to go down in intensity relative to this 0 dB line. Here's a zoom of that normalized direct path trace. By the way, we're going to save all traces at the end to show you the three cases all at the same time. Next, he's going to take an electrically large metal wall. He's placing it in the path, creating an obstruction to the waves. You can see how far it goes down in intensity. We're going to zoom in and you can see the intensity has gone down dramatically from the zero line. In fact, it's gone down between 15 and 20 dB compared to the direct path. It's feeble intensity and sets a stringent limit to the amount of edge diffraction. There's very, very little front scatter happening when you place a metal wall in the direct path. Now let's put the cloak cover on top of the metal wall. Here's a blow-up of what the cloak looks like. First, you're going to see the actual little fractals making up the metamaterial pattern, and then we're going to show you the sides and the top. Note the two layers of styrofoam used as mechanical spacers. Styrofoam has no impact on the cloak other than providing spacing for the fractal metamaterial. It's held together with blue RF transparent tape. Now watch what happens to the intensity when the metal wall is covered by these fractal metamaterial cloaking layers. Keep in mind the wall was down about 20 dB. Now you're going to see intensities have gone up dramatically. In fact, it's only a few dB to 0 dB in its peak relative to the direct path. Saving that trace to memory, we can now move ahead and take off the covered cloaking layers to see if we go back and recapture the feeble intensity of edge diffraction on the metal wall. Sure enough, you can see the live trace has gone back down to where it was before. We thus see a dramatic difference now going to get the direct path by removing the wall. So let's compare the three cases. The first is the direct path with no obstruction at 0 dB. Putting in the metal wall lowers the front scatter dramatically by 15 to 20 dB. But then adding the cloak cover on the metal wall raises the front scatter so that it looks very close to the direct path intensity. Ta-da! Front scatter now triumphs with the help of Fractal Metamaterials. Let's summarize what we have. The cloak produces front scatter at nearly the intensity of the direct path for roughly a 20% bandwidth with a metal wall which is electrically large. Note that this cloak need not be cylindrical nor spherical. Next, the front scatter is not being done by conventional means such as edge diffraction. It's being done with fractal metamaterials and evanescent surface waves. Finally, this cloak is simple to make and it is purely enabled by fractal technology. We hope you enjoyed this video, and we give you the very best wishes from the team at Fractal Antenna Systems.